going to talk today about Kubernetes probes. Now, these are tools that can make a service more reliable, more robust, and more resilient. But if not used carefully, they can ultimately make a service more unreliable, and they can even lead to catastrophic cascading failures. In other words, you can shoot yourself in the foot. And since this is Jay on the beach, my talk's going to be filled with pictures of footprints on the beach to evoke this podiatric theme. I want to motivate the types of problems probes can solve by telling a story from James Hamilton. This is a picture of James on his boat, which also incorporates the Kubernetes nautical beach theme. And James spent close to a decade living on his boat and navigating the world. You can read about it on his blog. Very interesting. He also writes a technical blog. James is a VP at Amazon, worked on Gravitron and Nitro, formerly Microsoft SQL Server, IBM DB2. Really amazing engineer who I admire a lot. We should check out his blog. And I recently got to hear him speak, and he told a story about Obidos, which was the original page rendering engine for Amazon.com about the mid-2000s. Now, this was a C++ monolith, and it was a 4 gigabyte binary, or approaching a 4 gigabyte binary, that had to run in 4 gigabytes of memory space. And it had to be restarted every 100 requests in order to keep it responsive. So this is years before Kubernetes, of course, but it illustrates this idea of measuring something about a service and then proactively taking action to make the service more reliable. This is James commenting on the impression of his colleague. Bruce Lindsay thought it was morally bankrupt engineering. James says, I loved it. We built a very reliable system out of very unreliable parts. And this is a wonderful notion that you can take individually unreliable components that can fail independently and then compose them into what is ultimately a reliable system. James says when you have systems that can fail, you can take more chances and you can innovate. And we do see these design principles in things like the Erlang programming language, reactive systems, and many of the cloud-native architectures that we work on today. But in trying too hard to mitigate failures, you can also shoot yourself in the foot, which brings me back to the theme of this talk. Now, the agenda for this talk is as follows. This is mostly to entertain myself and make myself laugh. I'll start with an introduction to Kubernetes probes. Then I'll describe how to shoot yourself in the foot. Once we've shot ourselves in the foot, I'll tell some stories about how to shoot yourself in the other foot. Once we've shot ourselves in both feet, we will go looking for even more feet. Then I'll take a look at clustered applications and how things can go wrong there. A cluster of feet, also known as a cluster foot. And finally, I'll look at a thundering herd problem. Okay, before we actually shoot ourselves in the foot, I'll provide an introduction to Kubernetes probes, what they are, what they do. So there's 3 types of probes. The first are startup probes, and they answer the question, is the container started and ready to serve traffic? The second are liveness probes, which answer the question, should the container be restarted? And then finally, readiness probes, which answer the question, should the container accept traffic? To understand how probes are executed, consider this deployment with a service backed by 3 pods. Of course, pods can be composed of multiple containers, and it's actually the kubelet that runs probes against the containers. And the probe can be run against a single container or any combination of containers that are in the pod. There's 4 types of probes: HTTP, gRPC, actually executing a command in the container, and then TCP. The exec and TCP, I would say, aren't that popular. They're largely used when you don't have external interfaces. gRPC is also relatively new. Most of what I'll talk about here today you can think of as an HTTP query against a service that has clients that need requests to be served. This is an example configuration for a liveness probe. Readiness probes and startup probes are similar. I won't go into them. I just want to emphasize that the probe is configured on the container in the pod spec. This is an example of the actual probe, so it's making an HTTP GET against a certain endpoint and port. The request will time out after a second. It will run every 3 seconds, and it will take 3 failures for the probe to be considered failed. Three consecutive failures. So let's look at each probe type in a bit more detail, starting with liveness probes. This is from the Kubernetes documentation. The kubelet uses liveness probes to know when to restart a container. For example, liveness probes could catch a deadlock where an application is running but unable to make progress. Restarting a container in such a state can help to make the application more available despite bugs. So the kubelet asks the container if it's alive. If the probe fails, perhaps the threads in the process are deadlocked, then the container is restarted in the hopes of restoring the service to availability. And the timeline looks like this. The probes are passing, then there's n failures of the probe, and the kubelet will restart the container in the hopes of making it available again. Okay, let's dive deeper into readiness probes, the second type of probe. Again, from the documentation, the kubelet uses readiness probes to know when a container is ready to start accepting traffic. And basically, if the container is not ready, the service load balancer won't route any traffic to it. The kubelet asks the container if it's ready to serve traffic. If the probe fails, then it makes the pod unavailable to additional traffic. Once the probe passes again, it'll start routing traffic to that pod. Note the containers here were not restarted like the liveness probe. They're just made unavailable to additional traffic. So it's just a routing. And the timeline looks like this. The container is ready. After n failures of the readiness probe, it becomes not ready. And after a single success, it becomes ready again. And then the final probe type, the startup probes. Again, from the documentation, the kubelet uses startup probes to know when a container application has started. If such a probe is configured, it disables liveness and readiness checks until it succeeds, making sure those probes don't interfere with application startup. So the startup probe is used to indicate when the container is ready to start accepting traffic, and it's similar to the readiness probe, but it's only called during startup and then it's never called again. So for example, a container could take a long time to start if it's loading a large cache into memory. Once the container is available and the startup probe succeeds, then it makes the pod available for service routing. And the timeline looks like this. The container is starting and it's not ready. Then the startup probe passes. From that point, the startup probe will no longer be called and the readiness and liveness probes take over. Startup probes, in combination with rolling updates, can identify configuration errors. And that's because by default, 25% of the pods must be available. So if you have a configuration error and you're rolling through, the pods will not advertise themselves as started, and you can go and identify configuration problems this way. So to summarize, liveness, readiness, and startup probes can make a service more robust and more resilient. Liveness probes avoid deadlocks. Readiness probes avoid overloading a service. And startup probes ensure availability before a pod starts accepting traffic. And they can also be used to guard against configuration errors. So these probes sound great. And when people discover them, they sometimes apply them quite liberally with the promise of making already very reliable services even more reliable. But it's pretty easy to unintentionally shoot yourself in the foot by doing this. At this point, I want to introduce Lauren's conjecture, which is really a conjecture about shooting yourself in the foot. And it comes from Lauren Hochstein's blog. And the conjecture is as follows. Once a system reaches a certain level of reliability, most major incidents will involve two things. The first, a manual intervention that was intended to mitigate a minor incident. Often see this during incident response. And the second is unexpected behavior of a subsystem whose primary purpose was to improve reliability. This is exactly what Kubernetes probes are, tools whose primary purpose is to improve reliability. So with that in mind, let's examine Kubernetes probes in the light of Lorentz conjecture, and the rest of this presentation will focus on ways that I've shot myself in the foot, or I've seen colleagues do the same. And I'll start with shooting yourself in the foot with readiness probes. So consider a deployment with a number of pods that each have a dependency. If the dependency becomes unavailable, maybe because it's processing a large batch job, recall that the readiness probe can be used to make the service temporarily unavailable so it doesn't receive any further requests and get overloaded. And then once the dependency is available again, the readiness probe will succeed and the service is available to additional traffic. But consider what happens if the pods are not independent and they all have a shared dependency. If the pods fail their readiness probe when the shared dependency becomes unavailable, all of the pods will become unavailable at exactly the same time, making the entire service unavailable. So the takeaways here, readiness probe will be called throughout the life cycle of the container in order to make pods temporarily unavailable. When originally Kubernetes did not have startup probes, and there was some confusion around whether readiness probes were called at startup or continuously. They get called throughout the lifetime of the pod, and it's important to remember that. If the readiness probe is verifying a shared dependency, be very conservative in failing the probe. Otherwise, you might make the entire service unavailable. And you should set the failure threshold greater than client timeouts. If the clients are willing to wait longer, there's no use failing the readiness probe. And don't use a readiness probe if you don't need it. If you don't need to become temporarily unavailable, I would avoid using readiness probes altogether. Okay, next, shooting yourself in the foot with liveness probes. So again, consider this deployment with a number of pods, each with a dependency. If a pod hangs accessing a dependency, maybe the threads have deadlocked, then Kubernetes will restart the container in the hopes of making the service available again. That's what a liveness probe does. But consider what happens again if there's a shared dependency and the dependency becomes unavailable. The liveness probe will fail on all the pods at the same time, and similar to what we saw with the readiness probes, but instead of just making the pods temporarily unavailable, it's going to restart all of them, making the entire service unavailable. This is especially bad if liveness probes fail quickly, and clients would be happy to wait just a little bit longer for their request to complete. Another way to shoot yourself in the foot with liveness probes is if the probe doesn't actually test the availability of the service. So perhaps it's just testing a TCP port or an endpoint that exposes metrics, but it's not actually the service endpoint. So it's important that, in this case, the pods can become deadlocked and unavailable, but the liveness probe is going to keep succeeding. It won't actually identify the problem. So it's important to test the actual functionality of the service that's important to clients. And that way, if the container becomes deadlocked, the liveness probe will fail, the container will be restarted, and hopefully the service becomes fully available. And a final way to shoot yourself in the foot with liveness probes is to try and handle too many errors. So you could trap errors such the container it's failed, but the liveness probe is going to still respond successfully. And in that case, it will never recover. But here I want to turn to the work of Joe Armstrong, who's the co-creator of the Erlang programming language, and a few quotes from his PhD thesis. Errors occur when the programmer does not know what to do. And then Joe asked the question, what kind of code must the programmer write when they find an error? And his answer to it was, the philosophy is, let some other process fix the error. But what does that mean for their code? The answer is, let it crash. And by this I mean that in the event of an error, then the program should just crash. I also want to return to James Hamilton, who I introduced earlier, when I described Obidos and how it was proactively restarted every 100 requests to ensure it was responsive. And he wrote this paper in the mid-2000s on designing and deploying internet-scale services. It's a wealth of knowledge for operating large-scale services. I highly recommend this paper. And in it, he concurs with Joe. Failure recovery must be a very simple path, and that path must be tested frequently. So for example, in Obidos, it failed all the time. So the failure paths were well known and they were exercised frequently. The best way to test the failure path is never to shut the service down normally. just hard fail it because it needs to recover from these situations anyway. This sounds counterintuitive, but if the failure paths aren't frequently used, they won't work when needed. So instead of complex error handling in our services, which is something I think we've been used to in the past, which could lead to bugs or potentially hang services, or even trying to detect that a container is hung using a liveness probe, just crash. Don't do any of it. Throw your hands up and crash. And let Kubernetes restart the container. In the words of Joe Armstrong, let some other process fix the error. Let Kubernetes act as a supervisor and use a simple mechanism, restart, in order to return the service to mammoth. So takeaways, don't check dependencies with a liveness probe. I think this is probably considered an anti-pattern. Use a startup probe or a readiness probe if you need to do something like that. If you find yourself tweaking the initial delay seconds in order to get readiness probes to work, you probably need a startup probe, not a liveness probe. You want to make sure you're actually evaluating the promises of the service, not just a metrics endpoint or something like that doesn't actually represent the health of the service. Make your error handling simple and make sure it's exercised frequently. And you want to make sure that you monitor and alert on pod restarts, because you might have a latent problem where pods are hanging and being restarted. You're going to want to address that, even though the overall health of the service is okay. And finally, don't try and do too much. Let Kubernetes handle failures with simple restart mechanisms. Just crash. Okay, the third type of probe, how to shoot yourself in the foot with startup probes. And this startup probes seem a bit more innocuous, I think, because they're only called at startup, not throughout the lifetime of the container, but it's still possible. So consider again this service backed by a number of pods. If a pod takes a while to start, perhaps the container is loading a large cache into memory, recall that once the container is fully loaded, the startup probe will then succeed and make the pod available to request. But if a pod takes too long to start, maybe the cache is now larger and the startup time of the container has doubled. The startup probe may actually kill the container before it has fully started. And then this could spread to other pods in the deployment. And then eventually the whole service becomes unavailable. So for a number of reasons, including persistent security threats, it is useful to restart pods on a regular basis. And this can also proactively identify changes in these startup dynamics. The Kubernetes descheduler is a way you can do this because it has a pod lifetime parameter. So for instance, you could set this to 1 day, and the descheduler will always roll through your pods, making sure that they're restarted after a day. The takeaways here, use a startup probe and don't rely on liveness or readiness alone. Kubernetes for a long time didn't have a startup probe, and people would have to have these careful configurations of liveness and readiness between startup dynamics and then steady state dynamics. And a startup probe has really addressed some of these, so make sure you're using a startup probe. Be very, very conservative in failing startup probes. I don't think there's any real harm in being extra conservative with them. You need to consider those exceptional system dynamics and changes in those dynamics over time, because you might need to adjust how your startup probes are configured. Otherwise, you might never get restarted. And I would regularly restart containers to identify these types of changes in initialization dynamics. And it's important to monitor and alert when pods are not ready. Otherwise, you might have one of these latent problems again, where the service as a whole is available, but pods are slowly becoming not ready and not recovered. Okay, so those are the basic ways to shoot yourself in the foot with liveness, readiness, and startup probes. But of course, they aren't the only ways. There's a few more. So looking for more feet. And I'll start with having a readiness probe, but no liveness probe. So if a pod becomes unavailable and not ready, but at that point then it hangs or deadlocks, it will never recover. And then this could start happening on other pods. So they're not ready and they're deadlocked until the entire service becomes unavailable. So what you want here is to have a liveness probe, so that when a pod becomes unready and hangs, then the liveness probe will identify that, restart the container, hopefully make it available again. Okay, the next way to shoot yourself in the foot is to have no monitoring and no alerting. So if liveness probes are failing and containers are being restarted, this is something you'll want to address, even if the service as a whole remains available. And then similarly, we've seen a couple times how a service can slowly degrade over time as pods are not ready when readiness probes or startup probes are failing. So it's important to have monitoring and alerting for these latent situations so that you can address the underlying issues. One way to do this is using kube state metrics, which exposes Kubernetes metrics in Prometheus format, and then called out fairly prominently in the documentation for it is the idea of monitoring container restarts to identify crashing pods or liveness probe failures, and the number of replicas currently available versus the desired number so that you can see pods that are not ready. Only takeaway here is monitor and alert on container restarts, and then pods that are not ready to help address these latent situations. Okay, next way to shoot yourself in the foot is with complex dependencies. So consider an ingress backed by a service, which is backed by a deployment with a number of pods, and then those pods call out into other services. Let's say one for authorization, one for inventory, and one for pricing. If the pricing service becomes unavailable, and that ends up failing the readiness probe, well then the whole service would become unavailable, whereas it could still have served requests for authorization or inventory. So if the service was split into two services, then the pricing service can fail, and it wouldn't impact the authorization or pricing requests. You could still be available for those. So be conservative failing readiness probes for services with complex dependencies, or avoid using them at all. And you want to isolate services to separate concerns so that you contain failures rather than spread failures. Okay, the next one, ingress controller reload. I think this one is a little less of a problem now, but it depends heavily on the technology that you're using for your ingress controllers, and I think it's a good one to be aware of. So consider an ingress that's backed by two services. For some ingress controllers, when a service becomes available or unavailable due to readiness probe failures or successes, it must restart and reload its configuration. And this is very disruptive to long-lived requests like WebSockets because they will be terminated. The way I observed this was actually someone was deploying a canary service into production. It wasn't even going to be called yet, but it was regularly becoming unavailable and reloading the ingress controller, causing a disruption on another service that had a long-lived WebSocket connection. So to prevent this, you can deploy dedicated ingress classes, and then if the state of the service changes, then it'll only affect that single ingress class and it won't disrupt other services. This is also useful for doing maintenance if you have, say, a dedicated set of WebSocket servers, but it does come with the overhead and additional complexity. So for services with long-lived connections, use dedicated ingress controllers. Okay, now let's turn attention to how we can shoot ourselves in the foot with probes for services that are clustered for durability or high availability. So this is what I'll call a cluster of feet or a clusterfuck. Consider a service with a set of pods, but instead of being independent, these pods actually are in a cluster and they gossip to determine leadership and then membership. I'm most familiar here with using Akka cluster, but I think the lessons apply equally if you're using RAP protocol or a cluster database like Cassandra. So if a pod is restarted, maybe due to a node failure or a rolling deployment, it can restart and become available from the perspective of Kubernetes, but it's not yet part of the cluster membership, and that means it can't actually successfully serve with requests. So what you want to do here is the startup approach should also consider cluster membership when it's deciding if a pod is ready to be routed to. In addition to this, for the startup probe and the readiness probe, we should often consider the mechanism the cluster uses to gossip because it's most likely going to be different from the endpoint for serving requests. And this can be helpful for detecting configuration or communication problems, especially during rolling deployments, because you want to ensure that the cluster always maintains quorum so that it can continue to serve requests. And finally, you should be very conservative with liveness probes with clustered applications. So say 2 pods are already being restarted because of a rolling deployment, or maybe they're unavailable due to a network partition. If you fail a liveness probe too eagerly, now the cluster no longer has quorum. And so instead of requests being potentially just a little bit slower, you've made the whole cluster completely unavailable. So startup and readiness probes should also consider cluster membership when you have clustered applications, and use liveness probes very, very conservatively in order to respect the quorum of the cluster. Okay, the final topic to conclude on a little bit more hopeful note. The final story I want to tell is a way that we used readiness probes in order to avoid cascading failures from a thundering herd. And it's a fairly creative use of a readiness probe. We'll call this thundering feet. Consider a service with a number of backing pods that need to handle a high volume of connections or requests. A slight increase in traffic or some other dynamic like a GC pause or even just restarting a single pod as part of a rolling deployment is going to could cause a pod to overwhelm its resources and then crash. Of course, that's only going to increase the loads even further on the remaining pods, to the point where another pod becomes overloaded and crashes, which increases the load even further on the remaining pods, and eventually this cascades through all pods, making this entire service unavailable. And in this state, it can actually be near impossible to get restarted, because as soon as a pod becomes available, it is overwhelmed by traffic, overwhelms its resources, crashes again. So one way to address this is to just way over-provision, or way more pods than you need. But this, is very costly, wastes resources, and you really only need those pods, just say during rolling deployments or a bunch of clients reconnecting in some kind of thundering herd. The way we solved this was to introduce a sidecar container that tracks metrics for the scaling factors of the application, and in our case, it was the number of connections. And when a pod is reaching its limits, then that sidecar fails its readiness probe, so that the service will no longer receive additional traffic, but it doesn't disrupt any of the existing connections. They stay connected. And once the service falls below this critical limit, the readiness probe succeeds again, and then it starts accepting new traffic. And graphically, it looks like this. So the pod's ready up to a certain point where it passes this critical threshold, that it's no longer ready, and then eventually it falls below another threshold and starts accepting traffic again with a bit of hysteresis, so it doesn't oscillate between these two states. And here's a graph of a rolling deployment we did recently. You can see some pods are being restarted, other pods are accumulating connections up to that critical point, and then no longer accepting new connections, and then they themselves are terminated and connections go elsewhere. So rather than risk cascading failure, we actually have a very, very predictable rolling deployment here, and we can do it without the expense of over-provision. So use readiness probes to shape traffic based on pod limits and metrics. But this is set empirically, so it must be adjusted over time. So just like we saw with shooting ourselves in the foot with startup probes, we may need to adapt here to changes in system dynamics or system resources. Okay, to conclude. And rather than a conclusion, I'll call these footnotes. But they keep with the theme. Kubernetes probes can make a service more reliable, but we need to remember Warren's conjecture, or we could end up shooting ourselves in the foot. So once a system reaches a certain level of reliability, most major incidents will involve an unexpected behavior of a subsystem whose primary purpose was to improve reliability. Kubernetes liveness, readiness, and startup probes are tools for improving reliability, but they definitely must be used with caution. Consider your system dynamics and how they change over time. Make sure that you monitor for container restarts and pods that are not ready, otherwise you'll have latent problems that need to be addressed. Be conservative with your probes, probably more conservative than you think you need to be. Separate concerns, because we want to contain failure and not magnify it. Make sure that you fail regularly. And that error handling should be simple and exercised frequently. And finally, don't use probes if you don't need them. Otherwise, you might end up shooting yourself in the foot, cascading failures, and things that you otherwise don't need. This presentation grew out of a series of blog posts that I wrote a few years ago. If you want this presentation and most of this presentation in written form, it's there. And I don't know if we're doing questions or we're skipping questions. Are there any questions? Okay.